So in this video we're going to look at magnetic flux density, and this is how we're actually going to work out the magnitude of the force on a current carrying wire in a magnetic field. Previously we worked out the direction of that force. We knew the current was in this direction, the magnetic field was perpendicular to it in this direction, and then the force was going to be in the direction of the thumb by using Fleming's left-hand rule. To be clear, we did all of this given that the current was perpendicular to the magnetic field. We could still use this rule in a way to find the force in any sort of wire in a magnetic field, even if it's not perpendicular, but that's certainly beyond what we need to be doing, far beyond what we need to be doing. So we're only going to consider when the current is perpendicular to the magnetic field. And then if we know that's the case, then we can find the force on the wire very simply just by using Fleming's left-hand rule. So we want to find the magnitude of this force. We want to find the magnitude of the force on a current carrying wire. We know its direction, now we just want to know how big the force is. So we're only going to think about a wire that is perpendicular to the magnetic field lines. I was saying we were going to do that in terms of direction, but also the strength of the force differs depending on the alignment of the current carrying wire with the magnetic field. At any other angle, so whenever the current isn't perpendicular to the magnetic field, the force is going to be less. So we've got F here, let's call this F1 for when the wire is perpendicular to the magnetic field. These black lines are the magnetic field lines. So these are our wires. We see the current is in this direction, and we see here the current is perpendicular to the field lines. The field lines are going in this direction down, the current's going this way along, so we have a right angle between them. So that tells us the force here, F1, that's going to be the maximum force. We call that F max. But we see that here, or rather F1 is going to be equal to F max rather. We'll work on the direction in a moment. In this case, however, we'll call this F2. We know this is going to be less than the maximum force because here it is not perpendicular. It's actually, we can look at it in components, and this is something we'll briefly touch on at the end just to work out, just to see how we extend this. We said actually this has got a bit that is parallel to them, right? There's got a bit that's going in this direction down. It's also got a bit that's going in this direction along. Or rather, better to think in terms of field lines. What we're going to see is we've got some of our field line is in this direction, some of our field line is going to be going in this direction. This is just resolving vectors. So we see is this bit here is parallel to this wire, so the amount of the field that is perpendicular to the wire, that's in this direction here, this component is less. That's why we're going to have less force. There's just less of our wire is less the component of this wire, forgive me, that is perpendicular to this field is less than the component of this wire that's perpendicular to the field. That's why the force here is bigger. That's kind of how that works. That means that F2, which is the force on this wire, is going to be less than the maximum force, right? Because in this scenario, it's perpendicular to it. The wire is completely perpendicular to this magnetic field. Here, the component of the magnetic field that's perpendicular to our wire is smaller. It's only this bit here rather than being this whole line down. We know because this side of this triangle is smaller than the side of this triangle. Therefore, there will be a smaller force on this wire.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.